Hello, everyone. My name is Sumaya Almani. I'm a PhD candidate at the University of California, Irvine. Today, I will present our work, which consists of a large-scale longitudinal study that tracks security vulnerabilities in native libraries and Android apps. Android developers opt for third-party libraries due to their convenience and reusability, since utilizing them saves time and effort. Native third-party libraries are prevalent in Android apps, especially social networking and gaming apps, which require special tasks such as 3D rendering, audio or video encoding and decoding. These tasks tend to be hardware intensive and are often handled by native libraries to improve runtime performance. The pervasiveness of native third-party libraries and their potential security implications call for a better understanding of the usage of third-party libraries in Android apps and its security implications. These security issues can, for example, affect up to 440 million users. A series of previous work has studied the outdatedness of third-party libraries in Android apps with a focus on managed code. However, these previous studies do not consider native libraries used by Android apps. We argue that the security implications in native libraries are far more critical for three reasons. They have higher chances of getting neglected. Native libraries are more susceptible to memory vulnerabilities, which are more difficult to exploit using managed code. Native libraries are also used pervasively in mobile apps. For example, 72.5% of the top 200 apps in Google Play contain at least one native library. Due to the pervasiveness and security issues associated with native libraries, we conduct a longitudinal study to identify vulnerabilities in third-party native libraries in popular Android apps and to study the speed at which app developers apply security patches. To achieve this, we construct a novel approach called LibRARIAN that takes an unknown native library and identify its version. We also introduce a new similarity scoring mechanism to compare native binaries called bin_square_sim. We build a repository of Android apps and their native libraries, which contains the top 200 most popular apps in Google Play. Using LibRARIAN and our app and library repository, we conduct our longitudinal study. The following figure shows the overall workflow of LibRARIAN, which enables the identification of native libraries and their versions. Given a set of binaries with unknown library names extracted from Android apps, and a set of known library versions, which we manually collected from open source software, LibRARIAN outputs a final set of versions detected for third-party native libraries by matching the unknown versions with known library versions. LibRARIAN achieves this by extracting 6 features from binaries, comparing these features against features from a ground truth dataset using a novel similarity metric, bin_square_sim, and finally matching against strings that identify version information of libraries, which we refer to as version identification strings. Our binary similarity detection is based on the extraction of features from binaries. These features include 5 metadata features based on the exported and imported functions, exported and imported globals, and library dependencies, and 1 data feature, which is applied as a second factor to either substitute the metadata feature in case the reported similarity score is low, or to confirm the reported score. These 6 features represent the code elements of a library that would be expected to change based on a versioning scheme that distinguishes major, minor, and patched versions of a library. Furthermore, these features are stable across platforms, regardless of the underlying architecture or compilation environment. Our similarity metric, bin_square_sim, leverages the 5 metadata features to compare 2 binaries by computing their common features over their unique features and reports a similarity score between 0 and 1. To identify binaries with low similarity scores, we leverage the version identification strings feature, which is a set of extracted per library version strings. For example, say an unknown library version extracted from an app has a similarity score of 0.3 when compared with OpenCV 2.4.11 using the metadata features. Given the low score, we search the version identification strings feature for specific keywords, such as the following two keywords, where the asterisk here represents the versioning scheme of OpenCV. We built a data set of heuristics by inspecting the binaries in our ground truth data set. For example, FFmpeg version information is found when applying one of the following regular expressions. To conduct our longitudinal study on third-party native libraries in Android apps, we apply our approach to binaries extracted from the top 200 apps in Google Play over 7 years. We track the version history of these apps from a large repository, collecting over 7,000 app versions. We found that 145 out of the top 200 apps in Google Play contain at least one native library, with a total of over 66,000 native libraries. These numbers, again, shows the extent of the pervasiveness of native libraries in the top apps in Google Play. To conduct our study of native libraries in Android apps, we answer the following research questions. I will focus on two of these in the upcoming slides. Please refer to the paper for more information. The goal of this research question is to investigate the extent to which native libraries of Android apps are vulnerable and remain vulnerable. We found that 53 out of the top 200 apps in Google Play contain a vulnerable library over approximately 6 years and 8 months. 14 of these apps still include a vulnerable binary up until the writing of this paper and are on average outdated by over 850 days. As a result, vulnerable native libraries play a substantial role in exposing popular Android apps to known vulnerabilities. The following table lists 14 apps, including some very popular ones like Amazon Alexa and Music, Facebook Messenger, DoorDash, which contained a library that remained vulnerable for an average of 859 days. The high severity and long exposure time of these vulnerabilities result in an ample opportunity for attackers to target these highly popular apps. The goal of our next research question is to determine the vulnerability response rate. We identify the duration between the release time of a security update and the time at which app developers applied a fix. A fix is applied either by updating to a new library version or completely removing a vulnerable library. We found that the rate at which app developers apply fixes is 10 times slower than the rate at which library developers release security patches. Our results show that it often takes years for app developers to update to a new library release, even if the existing release contains severe security or privacy vulnerabilities, placing millions of users at a major risk. The following table lists the top 10 most neglected apps in terms of the time to fix a vulnerable library. The time to apply a fix ranges from 588 days to nearly 5 years, affecting billions of users and leaving them at a substantial risk of having these libraries exploited. Some of these apps are highly popular and used by many of us, such as Lyft, Uber, Zoom, and Snapchat. This finding emphasizes the need for future research to provide developers with mechanisms for speeding up this very slow fix rate. To summarize, third-party libraries have become ubiquitous among popular apps in Google Play. Unfortunately, the pervasiveness of native third-party libraries in Android apps expose end users to a large set of unpatched security vulnerabilities. Our evaluation results emphasizes the market's need to record dependencies and alert developers of vulnerable libraries. We made our data set analysis platform and results available online to enable reusability and others to build upon our work. With that, thank you for your time and attention.
Okay, welcome back to this session on security vulnerabilities in different domains. So from JavaScript to Java with the second paper, from NPM to Android. We heard the presentation from Sumaya Almane too quiet in the library, and Empirical updates in Android apps native code. Come on, audience, do you have any questions? Okay, maybe I can just pick some curiosity that I have regarding your paper, Sumaya. So one is about this. Oh, actually, there is a question from Robert. I'm going to ask that one. Is asking, were there specific libraries that took substantially longer to update, perhaps indicating large changes in the API?
Specific libraries that took longer to update. So we one of the things that we was, I guess, out of the scope of this paper is we didn't really get to look into the exact libraries to get an idea of like what is the reason behind this slow update. So one of the future work of this paper would be to actually conduct some sort of like an interview or survey. We will reach out to the developers of these apps to get a better understanding of like the reasoning for this slow update. Yeah, so I would say that to answer this question, it would be actually like an extension of this paper.
Actually, I have a comment or yes, a follow-up on that question. Do you think that perhaps the slow time to fix has something to do with the culture when it comes to security and testing?
So we suspect that one of the reasons for the slow update can be, for example, like issues related to like regression, or usually their developers give higher priority to, for example, implementing new features. Again, in order to like answer the question to like why these vulnerabilities are outdated for this long, we need to reach out again to the developers to get a better understanding.
Definitely. Any more questions from the audience? I more related to this one, like I was saying, like when you pick the threshold for showing a low score of your new metric being to, what does low mean? Do you empirically get a threshold for low, or you just decided on?
So we decided empirically that 85% was the percentage that, at least from our results, showed that a library can be like an extracted binary is matched with a source binary, or like a binary from our ground truth. So yes, in order to we defined this specific threshold empirically.
Thank you. That makes sense. So there's a question from in the chat. He says, it seems that you used similarity metrics to identify native libraries. Could it be possible that some native libraries have been modified or even not released to solve security problems?
So that's an interesting question. I will actually quickly share
Sure. Go ahead.
slides, because it would be easier to. So yeah, we actually have an answer, I guess, to this specific threat to validity, which is the manual patching of security vulnerabilities. So LibRARIAN correctly identified 61.21% of patch level versions. Even for the majority that LibRARIAN didn't identify, we still managed to reduce the search space to 3 or 4 candidates. And we also believe that based on the results of our data set, we think that app developers are unlikely to manually patch libraries, given the fact that it took them a significantly long time to simply just update to a library version.
Okay. Well, and since you have your slides up, and in your presentation you kind of skip the result related to research question 1, maybe you can tell us a little bit more about it, what in terms of maybe precision or recall accuracy of your approach.
Sure. So in terms of the accuracy, we actually we conducted 2 types of analysis. We did a comparative analysis where we compared LibRARIAN against OSS Police, which is like the state of the art, or I would say that the tool that was the closest to what we're trying to do, which is inferring the versions of native libraries and then also conducting some sort of like an empirical study of these vulnerabilities. So when we compared LibRARIAN against OSS Police, LibRARIAN actually achieved a 12% improvement. So it went from 82% to 94% using our technique. We also conducted another independent analysis where we actually tried to infer the versions of the libraries in our ground truth. And we found that 91.15% of these libraries were correctly identified by LibRARIAN, so 824 out of 904 binaries.
Okay, and there's one more question from Salome Perez. How did you, first of all, she thanks and thinks that this work is interesting, and so do I. And she's asking, how did your approach handle native libraries?
So I don't really quite understand what she means by decompilation. One thing that we did take into account when we developed LibRARIAN or when we extracted the features is we tried to make it stable across all platforms, regardless of the underlying platform or also the compilation environment. So one thing that we did with LibRARIAN is we actually disregarded any features that are more platform or compilation related. So I would be more than happy to talk to Saloom in more details about her question in the discussion room. Yeah, this is my comment related to the compilation or the build features.
Okay, so we still have a couple of minutes. Let's see if there's more question from the audience. Oh yeah, there's one more from Chandungo. Is asking if native libraries are.
So the thing is, like, we extracted these binaries directly from Android apps. So again, we didn't really look at the exact compilation because, as I said, LibRARIAN and the features are agnostic to the underlying build or compilation environment.
Mm-hmm. So there's also another question from Savata-san. Thank you for your talk. I wonder if LibRARIAN is available for researcher to use on different APKs.
Yes. So we actually have 2 artifact evaluation badges. It's reusable and available. And LibRARIAN is available to be used by researchers. The data set is also available. Pretty much anything related to the results, the platform, the tool is available in GitHub.
Okay, so there's a final remark by Joshua, which points out that yes, native libraries are compiled to ELF rather than bytecode. But all right, so perhaps we can continue that discussion in the discussion room. Let me thank you, Sumaya, again for the nice work.
Thank you, David.
And the rest of the audience for the last paper of the session.
Thank you.